Hi class, we are moving on to chapter 8, and this first section in chapter 8 is 8.1, obviously. We're going to be talking about complex numbers, okay? So the entire section is on complex numbers, so before we get started, it'd be nice to get a sense of what complex numbers are. This may be a review for a lot of you, which is fine because complex numbers tend to be semi-difficult for a lot of people. So, again, this is what we're going to review, right? So the basic concepts, complex solutions of quadratic, so anything that's being squared, right? Operations on complex numbers, adding, subtracting, multiplying, dividing, and complex solutions of quadratic equations, right? So same thing as part 1. And then here, I know you can maybe hardly see it, but powers of I, which is also very important to discuss. So let's talk about what an imaginary number is, right? So an imaginary number is designated by I and is defined as the square root of -1. Now this is important because, as you know, you cannot multiply something by itself and get out a negative, right? That's what the square root sign is. It's saying what times itself will give you the number on the inside. And there's no way you can get a negative by multiplying something by itself, right? So 1 times 1 is always 1. -1 times -1 is still a positive 1, right? So our definition of the negative square root is this imaginary value I, right? So that if I were to multiply I times itself, I would get out a -1, right? So I squared is -1. So that's our solution to the negatives inside of a square root, was to create an imaginary value, which is actually not very imaginary at all, right? These things have actual multiple applications in real life, right? So they're not actually imaginary. A complex number is a binding of the real numbers and the imaginary numbers, okay? So we have A and B. We treat these as coefficients, right? A is the real part of a complex number, and B is the imaginary part. So a complex number is 1 part real, 1 part imaginary. So those two things together form a complex number, okay? So we write them again as the real part plus the imaginary part, right? So the B is how many imaginary units I have, and the A is how many real units I have, right? In the complex number A plus BI, again, just reiterating what I said, A is the real part and B is the imaginary part, okay? So let's talk about some basic concepts of the complex numbers. If I add, or if I want to say that two numbers are equal, then their respective parts have to be equal. So what do I mean by that? I mean their real parts have to be identical and their imaginary parts have to be identical, okay? So in order for two complex numbers to be equal to each other, the real parts have to be equal and the imaginary parts have to be equal, right? If A is 0, then that means that there is no real part and there is only an imaginary part. So if the real part is 0, then we fall back into the imaginary numbers, okay? Right, so 3i is strictly imaginary because there is no real part, okay? So again, complex numbers make up the real numbers and the imaginary numbers. Now if A is not 0, so it exists, and B is not 0, so they both exist and neither of them are 0, then we have a complex number, okay? So 7 plus 2i is an example. And a complex number written in the form A plus BI is its standard form, right? So whenever we write a complex number, we will always write it in its standard form, except for at certain points in time later on in this chapter, we will have a different form. But for the first couple of sections, we always will write these things in standard form. So you should have only one real value and one imaginary value. You should not have a mixture of real values and a mixture of imaginary. It should be one real and one imaginary value for standard form. Okay. Okay. So complex numbers, A plus BI, for A and B real values. So A and B are real values. They're the coefficients. A is the real number. B is the real coefficient for the imaginary part of our complex numbers. So what we're going to do right now is we're going to look at the complex number system and how it fits in with our number system in general. Okay, so when we are young and we first start learning how to count, we start counting by what's called the natural numbers, right? So 1, 2, 3, 4, things like that, right? So the natural numbers are whole numbers. They're positive. They go in order. And we generally say that they start from 1. Sometimes we say they start from 0, but we generally say they start from 1. So these are the things that you use to count with, right? So 1, 2, 3, 4, 5. There should be a little dot, dot, dot right here, but they're just showing that these things kind of go on forever. Okay, I don't know why they skipped to 37 and 40, but all numbers increasing by 1. Okay, the bigger portion of that, all right, so the natural numbers, they are nested within a bigger number system, which we call the whole numbers. Okay, so the whole numbers is the counting numbers, but including 0. So 0, 1, 2, 3, 4, 5, etc., etc., etc. Okay, now the whole numbers as an entire set, right, including the natural numbers, lie inside of a bigger set of numbers as well, which we call the integers. So if you notice, the whole numbers are all the positive values, including 0, but we don't have any negative values. So we use the integers to specify that we have all of the whole numbers plus their additive inverses, their negatives, right? So 1 and -1, 2 and -2, 3 and -3. So all the negative counting numbers are included in the integers, as well as 0, as well as all the positive numbers. Okay. The next number system that we have after that is the rationals, right? So the rationals is what you guys like to call fractions. So it's basically whenever you have an integer over another integer. Okay, as long as the integer on bottom is not 0, you are a rational number. So any integer, whole number, or natural number can be written as a rational number, right? So for instance, -2 can be written as -2 over 1, or it can be written as 2 over -1, right? So there's multiple ways to represent the same number in the rational number system. Okay, so the rational number system encompasses all of these 3 number systems. Now there is a bigger number system that creates the real number system, which is the irrationals. Okay, so the irrationals are the ones that are continue forever and don't repeat, like the number e, the number pi, square root of 2. Okay, so these are separate because these irrational numbers cannot make up any of these numbers. They're completely separate sets. I will say this, however, even though this is the number system we're most used to, this is smaller than the set of irrational numbers. The set of irrational numbers is a larger set of numbers than the rational numbers are. Okay, that's not entirely true. What we say is that the irrational numbers are actually more dense. Okay, so in between 0 and 1, there's more of these kind of numbers than there are all of these numbers combined. Okay, so they're densely packed together. All of these numbers, the rationals and all of their subsets and the separate set of irrational numbers together create the real numbers. Okay, so the real numbers are all numbers a plus bi, where the imaginary part is 0. Okay, when we come to the complex numbers, our first smaller set of numbers is the imaginary numbers, right? Where a is 0, but the b coefficient for the imaginary part exists. So these are all things that have no real part, but they do have their imaginary portion. Okay, and then the larger set of these is the non-real complex numbers, the ones that are complex, 7 plus 2i, etc., etc. So in reality, the entire system as a whole is a complex number system. Okay, because if the bi portion is 0, then you're in the real numbers part. Okay, if the a portion is 0, then you're in the imaginary or complex numbers portion. So all of these are really just complex numbers. So the overarching number system that we use is the complex number system. All right. So if we have an expression, square root of a negative number, then what we do is we separate this into -1 times the value under that square root sign. So what that allows us to do is to take that square root of -1 and just call it I, right? Because that is my definition of I, right? Is that I have square root negative 1. So I need to take that A value and separate it into two values, right? I need to factor out the negative 1 basically. And when I'm factoring it out, it's still inside of the square root symbol, okay? And since it's still inside the square root, what I can do is I can separate it so that I have square root of negative 1 times square root of A, and the square root of negative 1 turns into I. So I cannot have a negative inside of my square root, so I need to write it as an imaginary factor basically, okay? So let's do this as an example, okay? So if I have square root of negative A, I need to pull out that factor of I, and then of course simplify that square root of A. So if I have square root of negative 16, for instance, I need to pull out the I, okay? And then I can evaluate square root of 16. Square root of 16 is 4, so this turns into 4I, okay? Negative 70, same thing. I want to pull out the I, so I have square root of negative 70 is I square root 70. And then if I can, I would try to decompose 70 as much as possible, but the factors here are 7, 2, and 5, right? 7 times 10. So this doesn't break down at all, so I can't do anything with it, okay? Here, same thing. I'm going to pull out the I, so I have square root of 48. But square root of 48 can decompose. I can think of it as 4 times 12 or 16 times 3. 16 times 3 is probably better because I have a perfect square in there. So I can rewrite this as I square root 16 times 3. So 16 times 3 inside of the bracket, right? And then I can pull out this factor, which is a 4. So I got 4I root 3. Okay, so if you notice here, square roots are always at the end. Okay, even though we define this as a plus bi, right, and this b here is 4 root 3, the I always goes inside of the square root sign. Okay, same thing if this was 4 square root 3x, the x would go with the 4 and the square root 3 would go at the end. The reason being is if you put at the end, it's very confusing, and it can look like the I is inside of the square root or the x is inside of the square root. So we always write it clearly that I or x or z or whatever our variable is or imaginary portion is in the front on the left side of the square root. So if we have a square root, it's always the last thing that we write when we're writing our terms. Okay, so just so that we're clear on that, right? Now we want to solve equations. Okay. These are simple equations. My x squared term is isolated, so I'll square root both sides, and I'll get x equals the square root of negative 9, right? And now that I have the square root of negative 9, I need to do the same thing. I need to pull out my imaginary value, okay? And then I can take the square root of what's left over. So this will give me x equals plus or minus 3i, right? So very simple once I have it into this form. So again, when you're solving quadratics, ideally, you want to get x squared equals everything else. Unless you have other x terms that you can't get rid of, then you want to jump to the quadratic formula or completing the square or factoring or whatever other methods that we have, right? So my solution set is the set of these two numbers. So you can write it as plus or minus 3i, or you can write it as two separate numbers, 3i and negative 3i. It doesn't matter because this represents two values, right? So here, same thing. The only difference is that my value is not on the right side. It's on the left side with the x squared term. So obviously the first thing I want to do is move 24 over to the other side of the equation, okay, which turns it negative. So that now when I take the square root, I get the square root of a negative term. I can pull out the I and write this as plus or minus I root 24. And then I got to simplify this root 24, right? So this is the same as 6 times 4. 4 is a perfect square. So this turns into plus or minus 2i root 6. Okay. So again, when we try to break these apart, if we can, try to find the perfect squares so that it's easy to simplify. Or you can just break it down into factors and look for pairs. However you guys know how to do this is fine. Okay. And then that gives me my solution set for this equation. Okay. Now let's talk about a small word of caution. Okay, a lot of times people will see a square root of a negative times another square root of a negative, and they're like, hey, well, when I multiply these together, the two negatives on the inside of the square root multiply to be a positive, and they fail to pull out the negative term, right? The I term. And so you want to make sure that you're pulling out the I whenever you have a negative square root before you do anything. Okay, so again, let's just reiterate that. So when working with negative radicands, so things inside the radical sign, you always want to use the definition that square root of negative a is I square root a before applying any of our radical rules, right? So for instance, especially this rule, when we have c times d, if this was a negative c and a negative d, when you get here, you get a positive, but that's not going to be the correct answer, okay? So this is only true when both of the c's and d's are not negative, right? So if they are, you have to pull out this I and a second I, okay? So this is not true, right? Right, so if we do this separately, okay, you get a 2i times a 3i, which gets you 6 times I squared, which is negative 6, right? So we did the exact same operation and got two separate values. So you want to make sure you're being very, very careful here and you're pulling out your imaginary values first, or otherwise you're going to get very incorrect answers, okay? So here, these two things are not the same, right? So now let's multiply or divide as indicated. We're going to simplify each answer. Okay, so if I have root negative 7 times root negative 7, I will end up with 7 because I have two 7s, but I need to pull out the I first. So I'll have an I squared times 7. Okay. And I squared is negative 1, so you get negative 7. Right. Here, same thing. I'm going to have I root 6 times I root 10. And then I can look for common factors. They both have a 2 here. So I can have, I'll have negative 2. So 2i squared square root 3 square root 5. Okay. They like to go a very large roundabout way. But as I said before, square root 3 inside, square root 5 inside. So that gives me a square root 15. Okay. Here, I want to pull out the i's before I try to rationalize. In fact, I actually don't want to rationalize because if you notice, it's only a single term and a single term, so I don't have to rationalize the denominator. I can just write this all over one radical sign. But first, I got to pull out the I, and then I'll have square root of 20 over 2, or square root 10. So this will simplify to just square root of 10, right? So pull out the i's, and then I have square root 10. So regardless of if you decide to rationalize or not, or just think about this as square root of 20 over 2, you will get root 10, and the i's here cancel. Okay. So here I need to pull out the I first, okay, and then I can think about this as one large square root of 48 over 24, which is 2, right? So this turns into I root 2. So we want to simplify this quotient into standard form a plus bi. So obviously we're kind of leaning towards the quadratic formula because our answers to things in the quadratic formula will take this form when we have complex answers, right? So remember that this 4 can be separated to both terms, okay? This is going to be negative 8 over 4 plus square root of 128 over 4. So this is going to give me a negative 2, and then I 1/2 times this square root of 128, whatever that is when I decide to start to simplify this, okay? So we have to separate this into two separate fractions so that I have the real part from negative 8 and 4, right? So it has to go into a real part and the imaginary part. So negative 8 over 4 will give me 2, but that does not mean the 4 just disappears, right? Just because it's used on this portion, it gets used on both terms of the numerator, right? So negative 8 over 4 will give me a negative 2, and then this will be the second term, okay? So we can start to work on the inside. 128 is 64 times 2. 64 is a perfect square, so we will use that as our factorization, okay? So I know square root of negative 64 is just 8i because I'm pulling out the I, and square root of 64 is 8, right? So this simplifies to negative 8. This turns into 8i root 2. 4 is still the same. And I need to factor or distribute this 4 across, basically break my 4 out, right? So here I'm pulling out the 4 so that it can cancel. And I got negative 2 plus 2i root 2. Okay, so what I probably would have done from here is just notice that this is a negative 2, and then this gives me a 2i root 2. Okay, that's how I think about it. I generally don't factor the numerator if I have a common divisor to all the terms on the top. Right? Okay. So addition and subtraction of complex numbers. So when I'm adding and subtracting complex numbers, the real parts get added or subtracted together, and the imaginary parts get added or subtracted together. Okay, so we combine these things with their like terms, basically. So here A and C are both the real parts, so those real parts get added, and then I will add together my imaginary parts, and they will add together to be the new imaginary coefficient for I. Okay. Same thing when I subtract. Subtraction is just really addition. So I subtract the real parts, and then I'll add to that the subtraction between the imaginary parts. Okay. So now we're going to find some sum and differences. Same thing. I'm going to have 3 plus a negative 2. So I will have a 1. I'll have negative 4 plus 6. So then that will give me negative 4 plus 6, or 2. So I have 1 plus 2i. Okay. Same thing here. Negative 4 minus 6. So I can change signs, say plus or minus. So I'll have a negative 10 and have 3. And then the 2 negatives will turn into a plus. So I should have 10 plus 10i. Okay. Negative 10. Apologies. All right. So multiplying complex numbers. So when we multiply complex numbers, I'm taking something with 2 terms and I'm multiplying it times something with 2 terms. So I'm just going to use my FOIL method, right? Or whatever other method you have for multiplying binomials, right? So some people use FOIL. I use double distribution. It's all the same way. You can use your box method if you know the box method. That's fine. So here my A will distribute across this whole term. So I'll get A times C plus A times DI. And then BI will distribute across the whole term. So I get BI times C and BI times DI. Okay. So A times C, A times DI, right? And that's an imaginary portion. BI times C is an imaginary portion, so BC. And then BI times DI. That will give you a real value out because you're going to end up with an I squared. So that turns into a whole number, right? So this is the formulaic approach for that same thing. So let's go ahead and do an example. Okay. So for 2 minus 3i times 3 plus 4i, it's very clear here that it looks just like if I had x minus 3 times x plus 4, right? It's the same sort of format as when you are multiplying binomials. To expand a quadratic, it follows the same format, right? So whatever method you are comfortable with is fine, or you can use, again, go straight to this formula that we have here. So we're going to have 2 times 3, right? So I start to distribute the 2 across this term. So I have 2 times 3, and then I have 2 times 4i. Then I have negative 3i times 3, and negative 3i times 4i. Right? So now I can start to find these products and adding them together, right? So this is 6, 8i minus 9i, and this will give me a negative 12i squared, right? I squared is just negative 1, so that'll turn this to a positive 12, okay? And then I can start to combine my imaginary parts, so 8 minus 9i is negative I. This will turn into a positive 12. So I'll get 12 plus 6. So that's 18 minus I as my final answer. Okay. Here, same thing. So remember, when you have a binomial squared, you do not just square the first term and square the last term. This needs to be expanded to 4 plus 3i times 4 plus 3i. Okay, so I will have 4 times 4 squared, 4 times the 3i, and that will happen twice, and then I can square my 3i squared. So this is from the perfect squares rule, right? Square the first, square the last, multiply the two terms, and then double it. Okay, so from here I'll have 16, I will have 24i, and I will have a 9i squared. Okay, this is really just negative 9, so that gives me a 7 plus 24i. Okay, same thing here. This is the difference of squares. So this is when you can square the first term and square the last term and find the difference between them, right? So that gives me 36 minus 25i squared. 25i squared turns it into a negative, so a negative is positive. So this is really 36 plus 25, okay, which is 61. Okay. So if you want to do this on your calculator will actually do these for you. You just have to know where the I button is. So this is just an example of what it will look like when you do this on your calculator, so you can compare your answers. However, I do want you showing all work, so make sure you're familiar with what's going on here. Okay, but you can use this to check your answers to make sure they're right. You can always check your answers in math. So if you are not in the habit of that, then you should definitely get in the habit of checking your answers to make sure they're correct. Very important, right? So property of complex conjugates. So this is going to be very important for us in dividing complex numbers. So we want to make sure that we understand how conjugates work. So when you rationalize radicals, a lot of times you have to do radical conjugations. Okay, so here, if I have real numbers a and b, and that gives me a complex number a plus bi, okay, then the complex conjugate of a plus bi is a minus bi. And if I multiply those things together, okay, as we saw before, right, I can square the first term, and then I can subtract the square of the second term, because this is really the difference of squares formula. So when I multiply a complex number times its complex conjugate, I will always get a real number. Okay, there will not be an imaginary value. It will not be complex. If we look at this compared to what we had for a and b, when I multiply just two random complex numbers, I get a complex. If I square a complex number, I still get a complex number. Okay. However, when I multiply a complex number times its complex conjugate, right, I will always get a real number out. It's very important. This allows us to then start to divide values, right? So it's the difference of squares, right? So square the first term, square the last term, find the difference between them, but it'll end up being that you add the square of both values, because you're going to end up squaring an I, which will turn that negative into a positive, right? So you end up just squaring both terms and adding them together. Okay. So we want to write the quotient in standard form with a plus bi. So if I'm going to divide a complex number by complex number, I need to turn this denominator into a real value. Okay, so let's think about what a complex number is. It's a real value and an imaginary value pieced together. If I wanted to take something and divide it by 2, I know what that means. I'm going to take it and I'm going to break it in half into 2 equal parts. I don't understand what it means to take a number, complex or not, and break it into 5 minus I equal parts. That does not make any sense to me, right? So what I need to do is I need to bring this from a complex number on the bottom, or imaginary, and turn it into a real value. If this turns into, let's say, 12, I know how to break whatever this thing on top is into 12 equal parts. That's something that makes sense to me. So when we divide complex numbers, okay, we need to take this denominator and turn it into a real value. So how do I take something that's complex and turn it into a real value? Well, I multiply this whole number times 1. And the one that I choose is a number that should turn this into a real value. Okay, so I'll use a complex conjugate. So when I say times 1, that means I'm going to multiply the top and the bottom by the same value. Because if I multiply a fraction times 1, it does not change the value of the fraction. So I'm going to multiply it times 1, so the value doesn't change. But the way that I choose that one, I want to choose it in a way so that when I change the way it looks, but not the value, this bottom number is a real number. Okay, so top and bottom, I'm going to multiply times the complex conjugate so that this turns into a real value, but I'm multiplying it by 1 so that the value does not change. Okay, so top and bottom is times 5 plus I, so that I can do my little rule that we had, and I'm multiplying it by 1 so the value is not going to change. It's only going to change the way that it looks, right? So when I actually multiply this out, I'll get 5 squared minus I squared, which is going to give me 25 plus 1, so I'll have 26 on the bottom. Even though this numerator is weird, I'll know how to divide something by 26. I can break it into 26 equal parts, right? So the numerator we get by multiplying these two values out. So 3 times 5 is the 15, 3 times I is 3i, 2i times 5 is 10i, 2i times I gives me 2i squared. Okay, so now we'll figure out what these I squareds do, right? And we can start to add things like 3i plus 10i will give me 13i. Okay, so this turns into a negative 2 plus 5, so that's 13. 3i and 10i is 13i. The bottom is 26. So now I'm not done because it is not in standard form. It is in the form of a rational, right? A number on top, a number on bottom. So I need to separate this into two fractions. So 13 over 26 plus 13 over 26i. So this will give me 1/2 plus 1/2 I. Okay, 1/2 plus 1/2 I. Right? So that's how we divide complex numbers. So the goal, right, is to turn this into a whole number. So we use the complex conjugate. And the way that we do that is we multiply top and bottom by the complex conjugate. After we get an answer, right, in this form, we got to separate it into two parts. So we're going to separate this into two fractions. So the real part and the imaginary part, okay, because it does not always factor nicely. But that's what we need to do. We need to separate this into its two portions. Okay. So let's do this one more time with the second answer. So here it's a little bit easier, 3 over I. So the complex conjugate of this is just negative I. So I'm going to multiply top and bottom times negative I. So again, the complex conjugate is the same number. You just have a different sign in the middle. So the complex part is the part that changes sign. The real part, the A part, does not change signs, right? So here, 5 minus I, we multiply times 5 plus I. It's the part associated with the imaginary that changes signs. So here, we have no real part. We only have an imaginary part. So I need to multiply top and bottom times the opposite sign of the real part. So negative I times negative I. Okay. So I multiply. This will give me a negative I squared, which will turn into a positive 1. So this will turn into just negative 3I. Okay. So there is no real part. So, right, we're already used to looking at it like this. So we could say 3 over I is the same thing as negative 3I. I would much rather do math with this thing, as we have been already, than figuring out how to do math with 3 divided by I. Okay. Right. So again, your calculator will do all this stuff for you. But again, when I see this on an exam or your work, I need to see your work being shown. So don't rely too heavily on your calculator. But again, definitely use it to be able to check your work, to try to see if you made a mistake or not, so you can go back and fix your mistakes. Okay. So now we are moving back on to the world of quadratics. Okay. So here, if I want to solve this quadratic, I can't just say, let me get x squared alone and move everything else over to one side, because I still have an x term. Okay. So what I want to do is I want to put this in the standard form of a quadratic and either complete the square or use the quadratic formula. Most likely you're going to use the quadratic formula because nobody likes to complete the square. Although, if you are a math major or a physics major, you are definitely going to have to complete the square later on in your calculus courses, right? It's a skill that it's not super common, but there are definitely questions, especially when you start talking about conics and things like that, that you're just not going to get away from. In fact, my pre-calculus class, they complete the square all the time. So it is a skill that you want to make sure you don't forget how to do. But again, in this class, most of you guys are probably going to just use the quadratic formula, right? So first, let's go ahead and put this in standard form. So we'll move this 6x to the other side so we can set it equal to 0. So we have 9x squared minus 6x plus 5 equals 0. From here, we can try to factor if we can, but most likely we're not going to be able to factor. That's because we're in the quadratic section, the complex section of the textbook, so most likely it's not going to factor well. Okay, so again, here we're going to use with the quadratic formula. So a is 9, b is negative 6, c is 5. We can just throw that into x equals negative b plus or minus square root b squared minus 4ac all over 2a, right? So we just take our pieces and we throw them into the formula and start to work things down, right? So positive 6, 36 minus 36 times 5. So we have a common factor of 36 that we can start to try to pull out, which is what I would do if I was doing this by hand, over 18, right? So here we get negative 144, which is nice because then that's 12. So we should have a 12i here, right? And then now I want to separate this 18 to both parts. So 6 over 18 plus or minus 12 over 18 and simplify both of those fractions. Or you can pull out the common factor on top, which is 6, which will reduce this to a 3, right? So you'll have 1/3 plus or minus 2/3 I, right? Standard form, the real part and the imaginary coefficient, okay? So my solution set is 1/3 plus 2/3 I and 1/3 minus 2/3 I, right? So now let's talk about powers of I, right? So powers of I are actually pretty interesting. They follow a cyclic pattern, right? That goes in cycles. So if you want to know what your power of I value is going to be, just follow the pattern, okay? So I to the first power is just I, okay? I squared is negative 1 because it's I times I. I cubed is going to give you negative 1 times I, right? Because it's I squared times I1. So you're really just multiplying these two numbers together to get negative I. And then I fourth is the same thing as I squared times I squared. So negative 1 times negative 1 is 1. And then you repeat, right? So if I want I to the fifth, I'm going to get I to the fourth times I to the 1. So I will have 1 times I, okay, which is just I. If I want I to the sixth, I will take I fourth times I squared. So I'll have 1 times negative 1, which will give me negative 1. If I want I to the seventh, I'll multiply these two together because I have the power of 3 and 4. That will give me negative I. If I want I to the eighth, I'll take I to the fourth times I to the fourth, or 1. So notice it goes I, negative 1, negative I, and 1, and then it repeats. It goes these 4, repeat, these 4, repeat. The easier way to do this, okay, now that you know how it works, is whatever your power is, you take that power and you divide it by 4, okay? Whatever your remainder is, that is what you're looking at, okay? For instance, if I want to know I seventh, I take I7, I take 7 and I divide it by 4, okay? The remainder there is 3. So I go to I3 and that's the value that I have, okay? If I want I to the 35th power, I take 35 and I divide it by 4. That's 32, okay? Or the number is 32. It's 8, but it gives me 32. The remainder there is 3. So I to the 35th has a remainder of 35 divided by 4 has a remainder of 3. So I to the 35th is negative I, right? So I just look at, I just divide by 4, and I'm using the remainder to choose which value I need. Okay. If the remainder is 0, then your value is I4, is 1. Okay. So I want to simplify each power of I. So here I have I to the 15th. So again, 4 goes into 15 3 times, right? That's I to the 12th. The remainder is 3. So I to the 15th is really I cubed, right? And I cubed was negative 1. Okay. So here we're going to have to, here we have a negative power, so that's a little bit different. So we write the given power as a product involving I to the 4th, which is equal to 1, and then we look at the remainder. So I to the 15th is the same as I12 with the remainder of 3, right? So then all I have to do is look at what I3 is. Here they're just doing some fancy stuff with powers. I just take this and I just say I know that it's 1 because I to the 4th happens 3 times. So that's really just 1 times 1 times 1. And then I cubed is I squared times I1. But again, they're kind of doing a lot more than necessary. Just reference which one you need here, right? Okay. So you're going to get negative I, which is I cubed, which is what I said. Okay. I to negative 3, we have to apply the negative power rules, right? So here, we can separate this as times 1, and then add these together, which gives me I to the first power, which is just I, right? Okay. And there you go. Thanks, guys. See you on the next video.